Okay, this is the last activity for Unit 4, Motion of Particles in Electric Fields, and there are two topics here that are going to be on your next test. The one is the Milliken oil drop experiment. Now, this is a classic model to examine charged particles, so you might have asked things like, how the heck do they know what the charge is on an electron? And how do they study these small things and their charges? Well, one method they use, and this is a classic experiment, is the Milliken oil drop experiment. What I want you to do is get outside of just our content and look around YouTube for some good videos on this. Once we get into this in U4A5, I think I'll have dropped some hints by this point. There's a couple of videos that I really like out there that elegantly explain this. So if you're having troubles, just contact me. But what I want you to do is figure out what was Milliken trying to determine, how does the experiment work? So I want you to figure out how this works. Take the time to break it down and know how to do basic calculations. So it's going to be looking at number of charged particles and charges on particles. See if you can figure out some of the basic calculations for the Milliken oil drop experiment. You'll get one of these on your next test. The next thing you have to do is look at motion of charged particles in a uniform electrical field. And what I want you to think about here is conservation of energy. So when we were doing potential energy and kinetic energy, we used the formula potential energy is energy potential equals mass times gravity times height. Well, we're not dropping things anymore. We're not looking at the force of gravity, so we will not be looking at this. We're looking at electromotive force now. So our formula for potential energy is going to be the charge on the particle we're studying, Q, times its voltage. Where did we get this formula from? Well, in U4A4, we used change in potential is equal to change in the electropotential energy divided by the charge. So all I've done is rearrange this formula. So this is our potential energy formula, and hey, there's our kinetic energy formula. It's exactly the same, except now we're going to be looking at the mass of very small particles. For example, the mass of an electron is 9.1 times 10 to the negative 31 kilograms. We want to know how fast the velocity of that electron is moving, or what the velocity of that electron is. Let's take a look at a uniform electric field. Let's say we have a plate here, it's positively charged. Let's say we have a plate here and it's negatively charged. Back in U4A2, I think I said to you, hey, they're showing a diagram, and I don't know why they're showing it at this point. This is a uniform field. What does a uniform field mean? It means that the field is the same no matter where you are. So the repulsion from the positive to the negative is exactly the same. Let's say you have a positive charge in this positive field. And let's say that you drove it up towards this positive charge. This increases the potential energy in here. And that might seem a little awkward to you. It took energy for us to get this positive charge here, but think about it. If we drove this positive charge up here, what's going to happen to it? Because these two positives are so close, this positive charge is going to be repelled and go shooting towards the negative very quickly. So it's going to be repelled from the positive, attracted to the negative. Which one is going to have a greater speed? If we just had a positive charge here, or if we had a positive charge starting from here? Excuse me. What I hope you can see is this one's going to gain more velocity because it has more potential energy. It's going to have a greater amount of time and space to gain velocity as it goes across here. And this velocity is going to be much higher because it's going to have much higher energy potential. Remember, as potential energy decreases, kinetic energy increases, and we're going to get greater velocity. You may be wondering, like when we study circuit electrics, so if we set up a circuit with some loads and resistors and switches, we've got houses, we can understand where this is important. You might not understand where this is important. if you have an AC motor, this type of technology is extremely important in making these motors work. These electric fields are very important in AC, more so than in DC. Once again, if you're just interested in physics, look up AC motors, read up on Tesla. You'll see where this is used. TVs, especially the older tube TVs, use this technology. I have an old student, and sometimes we don't see all these cool jobs we can get into. He actually went to college. He did a chemistry program where he just looked at all sorts of machines or apparatuses that we use in chemistry, high-end stuff. And then he went to university and finished things off. Now he's working at a very major, well, I think he's in charge of the lab at a technology place where they look at paints and technology and paints. So they can paint things that they normally couldn't paint by applying charges to them. So this sort of technology would be used there, or this sort of information. Even in X-rays they use this. So we have to know the potential energy of the particles we're looking at, and that can help us determine the kinetic energy. Folks, you have two things that you have to get out of U4A5. You have to go through and understand the Milliken oil drop experiment. Then you have to look at a uniform field. This is content 1. Sorry, this is content 1. This is content 3. I've deleted content 2. It's a non-uniform field. And what you're going to be looking at is potential energy and kinetic energy within a field. We are done, Unit 4.